Today we will be practicing figuring out which is my limiting and which is my excess reagent. So my first example here, I have the combustion of methane, and my actual question states, identify the maximum mass of carbon dioxide that can be produced by a reaction of 24 grams of methane and 36 grams of oxygen. I've gone ahead and calculated the molar masses of all of the compounds that were actually mentioned inside of the question, so those are ready for me, and I can go ahead and start setting up my important conversion factors. Now, with limiting and excess reagent calculations, what we need to do is we need to run two stoichiometry problems, and then we will determine at the end which allows me to have more and which allows me to have less. I personally like to make sure that I maintain color code for that. So for my mass of carbon dioxide that will come from methane, I will have it in green, and the mass of carbon dioxide that will come from oxygen will be in red. I'm going to go ahead and establish the appropriate mole-to-mole ratios. So it is important to note that I am going to be establishing ratios between my reactant and whatever product I decide. I do not care about the relationship between the two reactants. So my first relationship will be between methane and carbon dioxide, and I'll go ahead and establish the those mole-to-mole ratios, and I'll establish them kind of down here. So let's see, I have 1 mole of methane for every 1 mole of carbon dioxide, and that means that I'm also going to have 1 mole of carbon dioxide for every 1 mole of methane. So that's the mole-to-mole ratio that I need for this green reaction. I'm going to go ahead and establish the molar mass for methane, and I'm going to establish it in green as well, just so I know where to look. And so I already have it calculated out, so I just need to write it out in conversion factor form. So 16.043 grams of methane for every 1 mole of methane, or for every 1 mole of methane, I'll have 16.043 grams of methane. And then, so I don't have to come back to it, I'm also going to establish the the molar mass ratio for oxygen, the molar mass ratio for carbon dioxide, and then I'll actually go ahead and do the mole-to-mole ratio for oxygen and carbon dioxide as well. So I will need the molar mass for carbon dioxide for both of the reactions, so I'm going to write it right in the middle, and I'm probably going to do it in purple so that I know it's a common thing, since this is the color that I chose earlier. So I will have 44.009 grams of carbon dioxide for every 1 mole of carbon dioxide, or for every 1 mole of carbon dioxide, 44.009 grams of carbon dioxide. I don't know which versions I'm going to need yet, so I'm just going to go ahead and do that. Now that I have this, I'll go ahead and I'll establish the mole-to-mole ratio that I'll need for the oxygen calculation. So I see that the coefficient of oxygen is 2, so that means I'll have 2 moles of oxygen for every 1 mole of carbon dioxide. And for every 1 mole of carbon dioxide, I'll have 2 moles of oxygen. And then finally, I'll establish this mole-to-mole molar mass, I keep saying mole-to-mole, molar mass of oxygen as a conversion factor. So 31.998 grams of oxygen for every 1 mole of oxygen. For every 1 mole of oxygen, it's 31.998 grams of oxygen. And now I have all of the conversion factors that I am going to need for both sets. I'm going to go ahead and I'm going to start with my mass that can be obtained from my mass of CH4. I just need to be careful that I am maintaining all of my correct values and I'm not mixing anything up. So I am looking for maximum mass, which means I'm going to be searching for grams of CO2 that can be produced by the reaction. Oops. I'll rewrite that. X grams CO2 that can be produced by the reaction of 24 grams of carbon dioxide is the one I'm going to do first. So 24 grams of methane. So now that I have grams of methane as my first setup here, I can go ahead and get started. I need to go from grams of methane to grams of carbon dioxide, which means I will need the molar mass of methane first to get out of grams. I need the version that has grams on the bottom, so that means I'm going to be choosing this version and plugging it in. Grams of methane cancel. I'm left with moles of methane, and I want to get to grams of CO2, so now I'm in an appropriate unit to go ahead and transfer from methane to carbon dioxide. So I'm going to do that with the mole-to-mole ratio, and I need the version that has methane on the bottom, so I'll choose this version and plug it in. Mole CH4 cancels, leaving me with mole CO2, but I want grams of CO2, which means now I need the molar mass of carbon dioxide. I need the molar mass of carbon dioxide with grams on the bottom, moles on the bottom, so I'm going to choose this one, and I'll plug it in. Moles carbon dioxide cancel, leaving me with grams of carbon dioxide. So that will go ahead and be solved. So that means I will have 24 times 1 times 1 times 44.009 divided by 16.043, 1, and 1. Just barely had enough room for that there. And now I'm going to go ahead and plug it into the calculator. So 24 times 1 times 1 times 44.009 divided by 16.043 divided by 1 divided by 1. Now I know these ones don't actually change anything, but I went ahead and did them anyway just for fun. And the number that I got out of that was 65.83656 4, 2, 3. And I'm going to go ahead and round to that second decimal place. So that would be 65.84 grams of that carbon dioxide. That would be my answer that I could produce based off of the mass of methane. Now that I have my answer for methane, I'm not done. I need to figure out how much I could have produced from this mass of oxygen. So I'm going to set it up again. So it says identify the maximum mass. So that means X grams carbon dioxide that can be produced by a reaction with 36 grams of oxygen. Currently in grams of oxygen, need to cancel grams of oxygen, so I'll look to the molar mass of oxygen, and I'll choose the molar mass that has grams of oxygen on the bottom. Grams of oxygen will cancel. That leaves me with moles of oxygen, but I want grams of CO2, so now I need to use the mole-to-mole ratio that has oxygen on the bottom. Moles of oxygen will cancel, leaving me with moles of CO2. And I have moles of CO2, but I want grams of CO2, so I'm going to use the molar mass of carbon dioxide that has the moles on the bottom. moles of carbon dioxide will cancel, leaving me grams. So that means since I have grams and I wanted grams, I can go ahead and plug this in. So this will look like 36 times 1 times 1 times 44.009 divided by 31.998, 2, and 1. And when I plug that into the calculator, I'm going to skip the ones this time for time's sake. I get the number 24.75660979. 6 makes me round up, so 24.76 grams of carbon dioxide is my final answer that could have been made from my mass of oxygen. Now this might be surprising to you as I look between these two masses. They are extremely different. Okay, I had a much smaller mass of methane initially going in, and yet I am able to produce significantly more carbon dioxide from that amount of methane than my amount of oxygen. Now, based off of limiting and excess reagents, I know that my limiting reagent is going to be nope, that is not true. My limiting reagent is going to be oxygen, because I can only produce 24.76 grams, and so my max mass is going to be that mass that could have been produced by the oxygen, so 24.76 grams of carbon dioxide is my maximum mass, because my limiting reagent was oxygen, which means that my excess reagent was that methane. Moving to this next problem, we have the double replacement reaction between aluminum bromide and potassium sulfate. And then my actual question asks if 1.24 grams of aluminum bromide react with 5 grams of potassium sulfate, what is the limiting reagent? What is the excess reagent? So I'm going to, just like I did last time, I'm going to establish all of my necessary conversions first, and then I'll actually start doing the problem. So I see that I have aluminum bromide and potassium sulfate as my two reagents that I'm caring about. I do not actually see a particular product that they care about, and I also don't see any specification about what unit that product needs to be in. That means I get to pick the product unit, and I get to pick the actual product that I'm going to be going toward. So this is a lot of freedom. I think I am going to pick the potassium bromide, if for no other reason than it's a little bit easier to write out than aluminum sulfate is, and, you know, lazy. So I'm going to go ahead and I'm going to establish the multiple ratios between these two. And so that will look like 2 moles of aluminum bromide for every 6 moles of potassium bromide, or 6 moles of potassium bromide for every 2 moles of aluminum bromide, AL. Pretend like that L made it in there before I wrote the B. The thing that I need to be really careful of here is, because it didn't tell me a product that I cared about, I just need to make sure that I'm being consistent, basically. If I did the mole to mole ratio between potassium sulfate and aluminum sulfate, well, now I can no longer really compare my results, because I'm not comparing apples to apples. It's a completely different problem, and so they're not comparable. So I need to just make sure that whenever I do my mole to mole ratio for this second problem, that I am picking potassium bromide as well. I'll go ahead and establish the molar mass for aluminum bromide, so that's going to be 266.69 grams aluminum bromide for every 1 mole. Now I have a couple of options for what I could do, since they didn't actually ask me for a particular unit for my answer to be in. All I asked was just that I determine what the limiting and excess reagents are. So again, I get to pick the end unit. And I'm going to go ahead and decide that I don't want to end in grams. I think that a gram to gram conversion just seems like a lot of work to me today. I don't really want to do it, so I'm not going to, which means that I do not need the molar mass of this product that I picked. I can just end at the mole of that product. So I'm going to go ahead and establish the mole-to-mole ratio between potassium sulfate and aluminum bromide. And again, I get to choose to do that because my question just wasn't specific enough, and I just didn't have a particular compound. I didn't have a particular unit for that compound to be reported in, and so I have a lot of freedom here, and why would I ever choose to make myself do more work than I absolutely have to? Then I'm going to do the molar mass of potassium sulfate. Okay, so now I have all of my conversions necessary, so I can go ahead and start actually doing the problem. Now, I decided that I wanted to stop at moles, so I didn't have to calculate molar mass, and so whenever I state my problem, I'm going to make sure that I'm writing out that I'm only looking for moles of potassium bromide and nothing else. And for this one, I am going to be figuring out how many moles of potassium bromide I could produce based off of 1.24 grams of aluminum bromide. And we're going to see how this goes. Okay, so I'm currently in grams of aluminum bromide. I need to get out of grams, which means I'm going to look at a molar mass of aluminum bromide, and I will select the one that has grams on the bottom. And I will plug it in. Grams aluminum bromide, grams aluminum bromide. Now I'm in moles of aluminum bromide, but I wanted moles of potassium bromide, so that means I'm going to go ahead and do the mole-to-mole ratio between aluminum bromide and potassium bromide. I currently have aluminum bromide on the top, so that means it needs to be on the bottom so it can cancel, so I'll select the appropriate mole-to-mole. Moles of aluminum bromide cancel. Now I'm in moles of potassium bromide, which is the thing that I said that I wanted, so I can go ahead and plug everything in. So that's going to look like 1.24 times 1 times 6 divided by 266.69 and 2. So 1.24 times 6 divided by 2, 66.69, and 2 gives me the very small number of 0.013948779. I'll round it to the third decimal place just because this number is so small. I just want to keep as many of my numbers as possible, so that's going to turn into 0.014. And then the only English left in my math, the thing that I said that I wanted, moles of potassium bromide. Okay, so I have my answer for what could be produced with that mass of aluminum bromide, and now I just need to go ahead and do it for what moles could be produced from this mass of potassium sulfate. So again, so I can compare apples to apples, I am going to stop at moles for potassium bromide, and I am reacting with 5 grams of potassium sulfate. Need to get out of grams, so that means I'm going to choose a molar mass with grams on the bottom. Grams cancel, leaving me with moles. I want out of potassium sulfate and into potassium bromide. Moles of potassium sulfate cancel, leaving me with moles of potassium bromide, which is something that I said that I wanted. So that will look like 5 times 1 times 6 divided by 174.259 and 3. And that also gives me a very small number of 0.057385845. I'm going to round it to the 3rd decimal place again, just to be consistent, and so that will give me 0.056, and then mole, I didn't have enough room, kbr. That will be my answer. So, now that I have my 2 things, I can go ahead and compare them. I can see that 0.056 is clearly larger than 0.014, so that means my excess reagent is from my red reactant, which is my potassium sulfate. And that means that my limiting reagent is from my green reactant, which was aluminum bromide.